binary input for addition and generate a sum and carry output. So half adder is a simple combinational circuit which take two binary input and generate 1 bit sum output and 1 bit carry output. So what does it mean by a combinational circuit? Combinational circuit means that the present output depends only on the present values of input. It does not depend on the previous values of output. Fine. So here my two binary input for additions are A and B. So using two binary inputs, how many set of combinations are possible? So we know that for n bit 2 to the power n number of combinations are possible. So using 2 bit 2 to the power 2, that is 4 set of combinations are possible. So here 4 set of combinations are 0 0, 0 1, 1 0 and 1 1. Okay, so simple binary addition we are doing. 0 plus 0 is giving me sum 0 carry 0. 0 plus 1 sum 1 carry 0. 1 plus 0 sum 1 carry 0. Now 1 plus 1 is giving me sum 0 carry 1. So in only one case, when both my two inputs are 1, that time sum is 0 carry is 1. Okay. Now we can find the expression for sum and carry using K-map method. So next we'll draw the K-map for sum. So this is the K-map for sum. So I want to mention that here we will write all the expression in SOP, means sum of product format. For whenever we are writing any expression in SOP format, so for 0 we will be writing its complement. Okay, I will show here. First we will put the input variables a and b in the K-map to find the expression for s. Okay, so in which cases s is 1? In these two cases s is 1. When a0, b1. So find here a0, b1. So here 1. Next is a1, b0. So here a1, b0. Okay, so here 2 1. So grouping of 1 is not possible. So what will be the expression for sum? Here we can find the expression. So for first one, here a1 b0. So a b bar. As we mentioned, for 0 we will be using its complement. Okay. For next one, it is a0 b1. So a bar b. So if we carefully observe this expression, we can see this is the expression for an XOR gate. Okay, a b bar plus a bar b. Okay, same way we will find the expression for carry using K-map method. So this is the K-map for carry. Now carry is 1 only for one case, when my both inputs are 1. Okay, a1 b1. So here a1 b1. Okay, so what will be the expression for carry? It will be a dot b. So from the expression we can see this is nothing but the output of an AND gate. Fine. So now we have find the expression for sum. We have find the expression for carry. Now from these two expression we can see we need an one XOR gate, one AND gate to design a half adder circuit. Okay. So the circuit is now this sum and carry, where my inputs are A and B. Okay. When these A and B are passed through an XOR gate, it will generate a sum. When these two inputs are passed through an AND gate, it will give me carry. Okay. Now, one limitation of this half adder is that we can add only two 1-bit numbers using half adder. If this is a multi-bit number, we can't use an half adder circuit. For this, we need a full adder circuit. Okay. So Next, we will show how to design a full adder circuit. So again, full adder is also a combinational circuit. Here, a full adder has three binary input. Two binary input are A and B, and the third input is the carry coming from the lower significant bit. Okay, so here how many inputs are there? A, B and C in. So we can see here three inputs are there. So how many possible set of combinations can be possible? 2 to the power 3 means 8 set of combinations starting from 000 to 111. Okay, so now again we will do normal bit by bit addition. Okay, here we can see 0 plus 0 will give me 0. This 0 plus 0 will give me 0. So sum 0 carry 0. Okay, bit by bit addition. Okay, next we will take one case when two among three input any two are 1 1. Okay, so here 0 plus 1 will give me 1. Okay, this 1 plus 1 will give me sum 0 carry 1. Okay, so here you can observe that when among these three input any of the two are 1, then sum is 0 carry 1. Okay, next we'll come to when my all the three inputs are 1. Okay, now 1 plus 1 is giving me 0 carry 1. Okay, this carry is going to here. Okay, so this 0 means 1 plus 1 is sum 0 carry 1. So this 0 plus 1 is giving me sum 1. Okay, so again we can draw the K map to find the expression for sum and carry. Okay, so this is the expression. We have to find the expression. So this is the K map for sum. Okay, so where S is 1 for these four cases, S is 1. So A0, B0, C1. So A0, B0, C1. Next A0, B1, C0. Okay, so again 1. Next case is A1, B0, C0. A1, B0, C0. Okay, fourth case is this when both the three inputs are 1. So A1, B1, C1. So here from the K map we can observe here no grouping of 1 is possible. Okay, so when we will write the expression for S, again we will be using SOP, sum of product format. Okay, so here no grouping is possible. What will be the expression for S? This is the expression for S. So for first one, it is A bar, B bar, C in. So here you can see A bar, B bar, C in. For next one, this is A bar, B, C in bar. A bar, B, C in bar. So likewise, we will write the expression for S. Okay, next we will write the expression of C from K map. Okay, so now this is the K map for carry. So carry is 1 for these four cases. This and this. Now we'll put the corresponding input variables. So from this K map we can see here grouping of 1 is possible. So this grouping, one grouping is possible. Next this grouping of 1 is possible. Next, this grouping of 1 is possible. So, three groupings are possible. Okay, now we will write the expression of C. Okay, so here you can see for the first grouping. Here, first grouping, this is 1, 1, A, B. So, this is AB. Next grouping, if we take this, okay, so what is common here? B, okay, and here C. So B, C. For the third grouping, for this grouping, we can see A is common, this one and this one, and C in. So A, C in. So we have find the expression for both sum and carry. Okay, now we'll simplify this expression. Okay, to design the full adder circuit. Okay, so here we are simplifying the Boolean expression. So from this first two term, we can take a complement common. So it will be B bar C in plus B C in bar. Okay, from these two expression, if we take A common, so this is B C in plus B bar C in bar. From this expression, you can see this is the expression for XOR gate. Okay, and this is the expression for XNOR, BC plus B bar C bar. So this is the expression for XNOR gate. Fine. Exclusive OR gate. Fine. So here again, if we write this in this form, again this is A bar. This total, if we consider this B, A bar B plus A B bar. So again this is a form of XOR gate. So this is A XOR B XOR C. Fine. So here, if we have a provision for 3 input XOR gate, we can directly give the input to a 3 input XOR gate, or either we can take the input separately and give the, suppose this is my XOR gate 1, this is my XOR gate 2. So here the output will be A XOR B. Fine. So and the input of this second XOR gate is A XOR B, and here second input is C in. So here my output will be A XOR B XOR C in. Fine. Now here we'll see the expression for carry. No further simplification can be possible. So here you can see we need 3 AND gates. For this 1, 2, 3. 3 AND gates and 1 OR gate. Okay. So here you can see 1, 2, 3, 3 AND gates and 1 OR gate for addition. Okay. We can design the full adder using 2 half adder also. So here you can see we can use 2 half adder in cascade form to design a full adder circuit. This will also give you the same result. So now I am going to show you how we can implement this circuit using logic gate simulator. Okay, this is theoretical expression. Now I want to see, is it giving me the same result? Okay, now I will show you using logic gate simulator. So first type here logic gate simulator. Okay, so I have already installed it. So one window will open. Okay, side by side will show the expression. Okay, so here this is my logic gate simulator. Okay, so such window will open. Here we can see that here are basic gates. We know which are the basic gates, and or not. Fine. What are the compound gates? Compound gates means using 2 or more basic gates. If we design a new gate, these are compound gates. Like NAND, we can design using an AND gate and one NOT gate. Okay. Next here we can see input output of gates are there. Okay. Now we'll first design a half adder circuit. So for one half adder circuit, we need one XOR gate and one AND gate. So here this is an XOR gate, just drag and drop. Fine. Again we need one AND gate, drag and drop. Fine. Now we need to input A and B. So here A, here B, and to output sum and carry. So sum, you can control C and control B. Okay, now we can rename it. Suppose this is my A, this is my B. Fine, this is my S sum, this is my carry C. Okay, now here A and B will be the input of XOR gate, and this will give me sum. Okay, when this A and B are connected to the input of AND gate, this will generate my carry. Fine. Okay, so here you can see red means 1 and white means 0. So here you can see A0 B1. Here you can see A0 B1 will give me some 1 carry 0. A1 B1 will give me some 0 carry 1. Okay, we can see this in waveform also. Here one oscilloscope option is there. So here you can see one oscilloscope option. Here when A, B1 straight line. So next change. Here, see here change is there. Okay, we scale down this A1, B0, sum 1 carry 0. Next make A0, B1. Here you can change, you can see the changes. Okay, when both are 1, so here both all the three these are A1, B1, S0 carry 1. Okay, so you can see the waveform also. According to the input it is changing or not. Okay, so here you can save this, save as, say we half adder 4. Okay, I am saving it as a name of half adder 4. Now we know that using two half adder we can design a full adder also. Now while designing full adder, okay, if we can take the half adder as a complete IC, so we don't have to draw the circuit again and again. So here you can find that import IC. When you click it, it will take the total circuit in this spreadsheet in one single IC. Okay, here you can find these are my user defined ICs. So here you can name it half adder 4. Okay, now you can save this IC, save as half adder 4 IC. Okay, save. Okay, now open a new window, import your designed IC. So import IC, here select all files. So what we have saved, half adder 4 IC. So here you can see half adder 4 IC. So now here your IC is active. Now just drag. So from this diagram we need how many half adders? 2 half adders. So here we need 2 half adders. What else we need? One OR gate. Okay, here OR gate is basic gate, so we need one OR gate. Fine. How many inputs we need for an half adder? We need 3 inputs and 2 outputs. So we need 3 inputs. A, Control C, Control V, then again Control V. So we need 3 inputs. Fine. Rename as A, B, okay. Rename as C. Okay, output we need 2 output. One is, okay, Control C, Control V. Okay, we need 2 output. One is our sum, okay, and one is our carry. Fine. So first added input is A and B. So first added input is A and B. Okay. Second added input is the output of first adder plus the carry C in. Here you can see the input of second adder half adder is the output of first half adder and carry in. Okay. Now here this will give me sum. Okay. Now the carry of first half adder and the carry of second half adder is going to an OR gate and generating the final carry. Okay, so we have make a full adder using half adder. So save it. Full adder 4 using half adder. You can name according to anything you want. Okay, so here save. Okay, now we will see the operation it is giving me proper. So A0, B0, C0. Okay, so A0, B0, C0. A0, B0, C0. This is giving me sum 0, carry 0. When all my three input are 1, sum 1, carry 1, sum 1, carry 1. Now A0, B1, C1. Okay, A0, B1, C1. Sum 0, carry 1. Red means 1, white means 0. Okay, so my circuit is functioning properly. Okay, so now we have designed a full adder using two half adder. Now next we'll design a half adder, full adder using only gates. Okay, now open new window. Okay, so we need XOR gate, 3 AND gate, 1 OR gate. So XOR gate is a compound gate, so copy. So here if you click, you will find isolate but no input. For other gate I will show you. We need to take AND gates. Okay, here you can, if you click right click, then you can find add input. So for basic gates you can add 3 input. For compound gate, for this is the limitation of this logic gate simulator, you can't take 3 input for compound gates. So we can always design a 3 input XOR gate using 2 XOR gate. So here control C, control V. Okay, so again another XOR gate. How many AND gates we need for carry? 3 AND gates. So control C, control V, control V. So 3 AND gates, and we need 1 OR gate. So this is 1 OR gate for carry. Okay, now we'll connect. We need 3 user input. So here 3 user input and 2 output, sum and carry. So rename S. Okay, this is carry, means final carry. Okay, this is my A, this is my B, this is my C in. Okay, C in. Fine. So first XOR gate input is A and B. Fine. This input is this output of first XOR is the input to second XOR, and another input of second XOR is C in. So this is giving me the final sum. Okay. Next for carry, what we need? We need for carry, what is the expression? AB plus BC in plus AC in. So here first AND gate, the input of first AND gate is AB. So A, B. The input for second AND gate is BC in. So here B, C in. Okay. The input for third AND gate is A, C in. A, C in. Okay. Here we need a 3 input OR gate. So we will add 1 input. Okay. Now connect the output of all these 3 AND gates to the input of OR gate to generate the carry. Okay. So this will give you carry. Okay. Now we will verify from the truth table. Here when all the, here you can see when all the inputs are 1, red means 1, 1, 1, 1, sum 1, carry 1, sum 1, carry 1, make A0, B1, C1. So A0, B1, C1. So sum 0, carry 1, make A0, B1, C0. So here A0, B1, C0. So this is S1, carry 0. Same you can see the waveform also. Here you can see the waveform change. This, the waveform will also change. See, okay, change this, the waveform will also change. Here you can find waveforms. Okay, so save it, save as full adder 4. Okay, save. Okay, so here we are here completing the adders, half adder, full adder, designing of full adder using half adder, and designing of full adder using gates. Okay, you can use this logic gate simulator circuit for simple operation, boolean expression, and flip flop generation also. Thank you for watching.